to begin with, let me say a couple of words about myself. Yeah, so I'm Mike. I'm a principal software engineer at Diligent, and I have like more than 10 years of experience in software development, doing it professionally. And throughout my career, I switched a lot of different areas. So I worked on the mobile development. I worked on the web front-end development. Worked with databases, with microservices, with event-driven architectures. Together with Yuri, we've built like a very high-load analytical system in our previous company. So yeah, and I worked with a lot of different web protocols, and today I hope to share with you like some good practices, like some good examples of like what can you use, like what protocols exist, like how you can use them, and what problems they solve. And surprise, surprise, I love hiking. I live in BC, and I love hiking. This is me and my daughter in Jasper this summer. This is the Edith Cavell mountain. I highly recommend, like very beautiful place. And if you ever visit Jasper, this is your must-go destination. All right, let's get to the business. Oh yeah, and a couple of words about the environment. So optionally, you can set up your own environment and follow today's workshop, because today I'm going to be like demoing a lot of stuff. So it is not a regular presentation. I will be showing like actual interactive demo. And I will show you some code. I will be showing you some like some services and how they work. It's completely optional. You don't have to like to follow it. And in fact, I think that it will be very challenging to follow the presentation and doing all this stuff at the same time. So I recommend you just use this QR code or take a link from the chat, and you can download the sources later. And try to run it yourself. It is very simple. You just need Docker, because everything there is configured to be running in Docker. Then I'm going to be using my browser as a web client, because the browser is a really good like web client, very sophisticated, supporting many different protocols, supporting many different techniques, and yeah, you can always use it like to test your network. And yes, just download sources later, and yeah, you can try to do it after the presentation. And okay, so let's start. So today we're talking about the protocols, and as you may know, like there are dozens of different protocols, and all these protocols are organized into so-called OSI model, where we have 7 layers. Like every lower layer is basically like isolated from any higher level. These layers stack on each other. That's why we sometimes call our network setup network stack, because protocol stacks on each other. And today we're going to be talking about web protocols, which means application layer protocols, which are like the highest level protocols that you actually use in your day-to-day work as a developer, because developers usually only care about like the very high level things. We want like just to use protocols to do our work, not to like implement some low level stuff. And yeah, and also protocols is not something that is set in stone. I mean, protocols always evolve, because our tasks evolve, because world around us changes, IT changes, we get more data, we get higher speeds, we get like more reliable networks that allow us to use like some new technologies, and that's why we see like different protocols like emerge over time. And today we're actually gonna like go over several different protocols and see how they solve different problems that that appear in the industry over time. All right, and but first and first, let's just start from the very simple example, because this is something like 101 thing. Let's start with the simple HTTP request and see like what is the HTTP request, because this is probably like the easiest thing we can start with. And here I'm switching to my demo environment, and I will be actually showing you some code. Can you tell me if you see this well? If the zoom level is fine, like scale is fine? If I open the file, can you see the text?
Yeah, it looks good.
Cool. All right. Yeah. So I'm going to be going through this the demo examples throughout this presentation, and actually every file has this header. I posted my contacts here. I mean, if you will be trying it later on your own, you can always contact me over email or LinkedIn. I also posted this meetup link so that you don't lose it and come to the next one. Yeah, and in this first demo, I will be just showing like very simple REST API. It has like 3 different methods, like 3 different get methods, and it just returns some predefined data, just like to showcase the HTTP itself. And here I have my SPA based on React and Material UI, nothing fancy. I mean, don't judge my design skills, because this presentation is not about design, it's about network. And actually, you should be paying more attention to this DevTools tab, because like all the stuff that we're talking about today will happen in the network, not in the UI or somewhere. So can I start? So I have this first demo. When I click this button, it's going to make 3 HTTP calls to my API, and it's going to grab some data and display it here. So I click it. You see data is rendered on my screen. It is a profile, location, and some history, like which is the list. And here you can see that it actually made a few HTTP calls. Actually, let me add something here so that we can see it better. And the protocol. Yeah, so actually Chrome DevTools can tell you a lot about your request. So first of all, you can understand like what protocol was used to do this request. And here you can see this HTTP 1.1, which is, I mean, when I say HTTP, I will mean HTTP 1.1 or like HTTP 1, because we also have HTTP 2 and HTTP 3, but we will distinguish between those. You can also see like how much time did it take to load your resources, what was the size of the request, and you can also see the timeline of the resource showing you like what was going on in this particular HTTP request. So you can see that there was like some initial connection negotiation, like DNS lookup, requesting servers, downloading data from the response, and then basically connection is done. And for every such connection, you can see very detailed information about what was requested and what was responded back. And HTTP is a stateless protocol, which means that all the information for this particular request is always passed as a part of request. There's no state. Everything that clients want to send to server is included into every HTTP request. If you have any state, it is usually passed through cookies. We don't have any cookies here, but I mean, you may have some. And yeah, so important parts here are like what was the destination, what is the response status for your HTTP request, what is the response headers that server responded with, what was the request headers that a client passed to server to like to give some context for this request. And you can see that the response is in a JSON form, or like all 3 API endpoints basically serve JSON. You can see the response payload itself. You can always see like what was transferred back in the body. So you can see that for profile, it was, I mean, whatever I put here, I mean, whatever I hard code here is returned back. For location, the same. And then for the history, there's a list of some events. And yeah, so that's actually like a very simple example. And yeah, so let's move on. And we come into the first networking problem. So I guess everybody encountered the problem where you have to transfer a lot of data over HTTP. It might happen, like, for example, if you implement any sort of like exporting, or like you implement some in-memory data processing in your service. And actually, please comment in the chat if you ever got OOM during network communication in your service. And actually did. I can tell you that it happens quite a lot, because not every file can be fit into memory. Like obviously 900 gig file, it cannot be put into memory and served. And the solution to that, I mean, one of the solutions that you can use is to use HTTP streaming. HTTP streaming was introduced in the HTTP 1.1, and it is implemented using a special transfer encoding header in your HTTP request. So basically, you can, I mean, your server can specify that it's actually going to serve a stream of data, not the bump of data. And in the next demo, I will show you like what's the difference between this naive data transfer using the blob of data and the stream. So let's move on to the next demo. Here's my second demo. Let me show some code. So in this example, I have this sample JSON data, which is actually not 900 gigs. It is only like 20 megabytes because I don't want to bring my environment down. But even a 20 megabytes file will show you how streaming is different from the naive in-memory transfer. And I have my server here that actually have two endpoints. First endpoint is called blob, and in this case we just read the file into memory, and then we send this data over, which means we load this file. And in the stream endpoint, we open a stream to the file, and we pipe it into the HTTP response stream. And this is a conceptually different a type of IO. So like streaming IO is always different from from how to call it, like from the classic IO. And it is not only related to network. If you use any framework or like any library like Node.js, you know that there are like two sets of APIs of like input-output API. There's usually the regular IO and there is a stream IO. And we'll see the difference between them very soon. So let me just go back to my SPA. Here I have three buttons. The first button will just load this blob of data, which means it's gonna take this in memory blob. It's gonna transfer it over the network, and the client will just treat it into memory. And here I want to show you some profiler because we need to pay attention to memory. This is my client-side profiler for the JavaScript VM in the browser. And here is my Node profiler, which actually connected to my API. And you can see the Node processor, and you can see the memory here. Now let me just click on the button. I'm clicking on it. You can see that this blob is actually loaded. Yeah, let me just close this. So it is like 26 megabytes. It took 3 seconds to load. But the most interesting part here is that if I see at the memory here, you'll see that memory actually spikes in both in the browser and in the server. Oops, sorry, I clicked the wrong one. This. Yes, memory spikes in both environments, which means we just like utilize on the memory. And moreover, you see that 20 megabytes of payload actually creates a spike in like 200 megabytes. That's because JSON parsing and JSON transfer requires a lot of additional memory in addition to your payload. And now, if we click the second button, all of that will be transferred as a stream. So let me just go back to network, clear this up, and just click this. You see stream is happening that was transferred. You can see that in the response, there is this like a transfer encoding header that actually defines that the server is going to respond with the stream, not with the bound, not with the blob. And on the timing diagram, you can see that actually there was no waiting for response. So stream started right away, which means when you streaming, you solve one more problem, and because you don't split your initial data loading on the server side and the transfer. So in first example, these two operations happens one after another. In this example, they happen in parallel. So a file is read from the disk, and at the same time it is transferred over the network, and you can see that server memory does not spike anymore in this case, because we don't read actual data into memory. We only use a buffer for the stream to load a chunk of data and transfer it right away. But on the client side, you can still see the spike, and that's because we actually, on the client side, we still load all that into memory. And well, this is, I mean, this may be required by use case at some point, but I want to make another distinction between stream transfer and stream processing, because these are like two different things. You can transfer your data in a stream, but if it ends up in the memory on the client side, you don't do stream processing. So stream processing means that you pipe your stream into some client side logic. For example, you may have some stream friendly format like CSV or JSON-L, and then you pipe your stream into your stream parser, and then your stream parser just processes this data on the fly and download it into memory. And in this insert button, I have my subscription to the stream. I don't do anything with it. I just print it into the screen, but you may as well use it to stream parse your data and download it to disk right away without using a client-side memory. So if I click this, you see that my data is transferred in the chunk. Like every chunk is processed separately. So if you pipe this into the stream parser, you will get stream processing without memory utilization. And you can see that a client-side memory doesn't spike anymore. So it doesn't matter how many times I click on this, you will see that the client-side memory is now fine, and you don't get out of memory event. Is there any questions about this example? Any comments?
Two questions.
Okay.
In the chat.
In the chat. Okay.
Yeah, one of them is related to JavaScript frameworks that you're using.
Mm-hmm. Yes. Yeah. Right. So yes, the backend framework is Node.js plus Express. I use Express because I mean, it is like probably the most popular Node.js server. It is not that I think that Express is the best choice. It is just the one that everybody is familiar with. That's why I chose that. And we don't use anything. I mean, we don't do anything fancy here. So Express is fine. And on the front end, right, it has Material UI and React, and then React scripts for rendering and like bundling and everything. Okay, and the second question, does this profiler work with the Node.js server? Right, so what I'm showing here is that here in the Chrome DevTools, this memory tab is actually like the browser side profiling. So this one is connected to the browser JavaScript engine. And but now Chrome also supports integration with the Node.js. So here in Chrome, if you have any Node.js process that actually runs with the inspect parameter, I will show you here. So in this like demo server 2, if we go to my package JSON, this second demo is actually running with the special, with the profiler attached to it. So that's how you attach your profiler. I have to put this 000 IP because I'm running it from Docker, and for the Docker network, it just required to have like this this gateway. But if you're running it locally, you can just put like inspect, and by default, it's going to be on localhost. And then as soon as you run this process in Node, your Chrome browser will actually have this button active, and when you click on it, it's going to open the server side Node.js profiler, and this one shows the server. You can see that this JavaScript VM instance is actually my Node.js application, which runs from this like demo2 streaming server JSON. And you can also like take snapshots. You can like check allocations. Pretty much everything that you can do in the browser, you can also do in this profiler, and it is integrated into Chrome. You don't need to set up anything extra.
Looks
Does
like
that answer the question?
Sorry?
Okay, one more question. CSV works well with stream. Can you explain what method works well with what? Okay, yeah, that's a very good question. So basically, for your format to be to be like streaming friendly, you need something that delineates chunks of data. And for example, in CSV, it is very simple because every row in CSV is actually delineated by the new line, sequence. So like every row there, it can be passed independently, and you can render row by row in the CSV. Another example of it is so-called JSON-L format, which is actually like a regular JSON, but instead of just instead of passing the array of objects, you pass. Okay, I mean, probably just open it. So JSON-L. Yeah, so which stands for JSON lines, and the format itself looks like examples. It looks like this. So every row in this file actually represents an object. There is no comma. There is no like square brackets around it. So, and now again, every object in your transfer is actually self-contained and delineated by the new line character. And I mean, maybe there are other like stream-friendly formats you can come up with. I mean, out of my head, I just don't remember them all. But I mean, you need to look for the easy delineation between chunks of data. For example, in regular JSON, because you have this like structure as a dictionary, and you have all these commas and like all the separators. JSON itself is a single piece of data. You cannot easily split it, although there are stream parsers for JSON as well. So basically, like there are some parser libraries that can support streaming. So I mean, they can basically parse your JSON on the fly, providing you some callbacks when your object is fully received and you can process it. It is just more tricky than just parsing CSV. Okay.
One more question.
Yeah, I see. Is there a way in Shibit to pause the stream? I think you need more data later. Well, I mean, the pace of the stream is actually controlled on the server, because a server basically pushes your stream to you. And I mean, usually there's no way on the client side like to stop the stream unless you have some back pressure mechanisms implemented on your client. And actually, we will get to this problem a bit later when we will be talking about gRPC and in the bidirectional streaming. But in HTTP1, I don't think there is easy way to actually control the pace of the stream.
And by default, if the stream was interrupted, it's not possible to continue from the same spot, right? It's just to open a new stream.
By default, yes. By default, yes. It basically means that your connection failed halfway, and on the HTTP, I mean, on the client side, it's going to be like entity truncation error, or like, I mean, usually in the most of web servers that stream this data, it would be like entity truncation, like unexpected entity truncation error, which means stream was like interrupted unexpectedly. Okay, I think there's no other questions for now. Let's just proceed. And we're moving on to the next problem, which is like actually one of my favorite problems. And I first came across it when I was doing some web front-end development. And this head of line problem, or like a head of line blocking problem, is actually the generic problem for the networking, and it has two flavors. It can happen on like transport layer, and it can happen on the application layer. Here in this particular example, we're talking about the application layer, which means like HTTP, a head of line blocking problem. And this problem is related to the fact that you have limitations in your client. So for example, if you use any mobile device, or if you use a web browser, you may or may not know that actually number of connections that browser or mobile device can use is limited. It is not infinite thing. And if you have one particularly slow connection on your server, it can actually block other fast connections. And so like and all this fast requests can be blocked by this small connections. Which is in the head of line of your HTTP pipeline. And yeah, so let's just jump to the demo, and I will show you how this works. Demo number 3, head of line problem. So here in this demo, what I'm doing, I have my server here, which actually just serves like a very simple style CSS file, and I will explain why I put this particular payload later. It is needed for consistency with some later demo that I don't control fully. But okay, just for now you can see that it actually transfers some CSS on request, and I specifically put some delay here, so it actually simulates a slow connection. So my request will take from like 500 milliseconds to 1 second and 500 milliseconds randomly. And on the client side, I'm requesting 50 resources in parallel. And I would expect, if I don't know about this limitation, I would actually expect that all my resources are loaded in parallel. Like what's the problem? Why not? But if I click on this button, you will see that it starts loading my style. I use some index just like to make it unique. But you can see that, okay, it starts loading, and you can see that something is not quite how you expect it to be. You see that here we have this waterfall, and some resources actually start loading much later than you would expect. And if you scroll further, you will see that, okay, so there's quite a delay here. And if you sort by the connection ID, you will see that actually we only have like 1, 2, 3, 4, 5 or 6 unique connections here, and that's what I'm talking about. Like all the browsers, depending on the type, are limited to like 5, 6, or like maybe 7 connections. I mean, it depends on the browser, but in general, a particular instance of your browser, like your browser tab, is actually limited in the number of connections that you can use. And you can see that every connection actually loads all the resources sequentially. When it's done with one resource, it starts another one, and so on. And it is the case for all the connections. And that's why instead of having like 1.5 seconds for all the requests, we actually end up with like almost 10 seconds of load. And yes, so that is the problem that I wanted to show. And next, I will show like a couple of ways like how this problem is actually solved at this point. But before that, is there any questions about this demo? Okay, then let's just jump to the first thing. And yeah, I want to talk about GraphQL here, because GraphQL is not really like the best solution for this problem, but it is something that you can consider. GraphQL is not a protocol by itself. It is a sort of like a wrapper around HTTP that allows you to query your data from the predefined schema. It was developed by Facebook around like 2012, even before HTTP 2 was actually introduced. And at that time, Facebook was trying to solve this particular problem of like limited resources and limited connections. And now, I mean, you can think that GraphQL is great, or you can think that GraphQL is like a very bad idea. But from the networking perspective, it is just a hack around like this connection limitation, because in GraphQL you actually transfer all your data over a single connection. And I will show you how that works. Let me just first show you code. So here in demo 4, we still use the same Express server, but we also use the Express GraphQL plugin that actually just enables GraphQL at top of Express. And here we have our GraphQL schema defined, which I mean, I won't explain it in too much details. If you want to read about GraphQL itself, it is not the topic of this presentation. So, but basically in GraphQL, you just define your API schema in advance, and like everything is strongly typed. You can see all the resources that you can request, and you can see all the types of these resources. You can filter by fields. You can request only a subset of field from every resource. You can see that our API is still same. We still have the profile, we have the location, and we have the history list, which has the data, and this data is the list of history entry, which is in its turn have all those fields that we saw before. And now, like our top level resource, which is called query, actually can serve all these three sub resources in our resolver, and our GraphQL resolver is just, yeah, I mean, again, all this hard coded data as before. This is exactly the same as in the demo one, but in this case we are going to serve it over GraphQL. Now I go to my demo number 4, GraphQL, and let me clean this up. I click this, and it's gonna make a single query. You can see that it doesn't have this 3 HTTP calls anymore. It actually uses a single GraphQL call. And if you go to payload, which is the request, you can see that it actually a special GraphQL format, which is not a JSON. It is not like a text format. It is like something unique for GraphQL. It has its own syntax. There are libraries that can help you build this GraphQL request, because it can be tricky if you don't know the syntax itself. But you can see that we basically request all three resources in the same request. So we request profile, and we request only name and title. For location, we request only state and city. And for history, we basically request everything. And in the response, it serves all the data as a single piece. So it sends me all 4 resources in the same, all 3 resources in the same response, using only one connection. And this approach can be beneficial if you, for example, if you build a mobile client, or you're working with some like very slow network, or like very lossy network, for example, some like old generation mobile networks. So you may choose to use GraphQL just like to make your connection more reliable and less resource consuming. That's basically the main point from the networking perspective. Any questions about this example? Okay, I guess not. And let's move on. And the next slide, and actually like the next solution for that head of line problem, and actually the proper solution was introduced with the HTTP2, which is the evolution of the HTTP. And like as any new version of some protocol, HTTP2 tries to solve all the major challenges with the previous version of the protocols. And actually one of the major challenges with the HTTP1 is this head of line problem, and like inefficient TCP connection utilization, because every query in HTTP1 is served over a separate TCP connection, which is like very resource consuming. As you saw, browser is limited in terms of like how many connections you can use. Some connections can be slow, which basically makes it very inefficient, because HTTP1 was created in a time where there were only like static files. You make your request, you get the file right away. There's no delay. Everything is very fast, and you don't have to bother. But now in the modern world, we actually have like some long running queries. We have some background processing. We have downstream services that actually also have their own latency and their own delay, and this kind of like inefficiency in TCP actually becoming a problem. And one of the major features of HTTP2 that I'm going to talk about today is the connection multiplexing, which means multiple requests can be served over one TCP connection instead of having a dedicated HTTP connection for every request. Yeah, let me just jump to my demo now. I have my server here. And again, I use Express, and I use a special library that actually implements HTTP2. I mean, I use Speedy because it is like the oldest one and like the most supported one, easy to work with. But there are other Node.js library that implement HTTP2. For example, like native HTTP2 can be also used. It is just harder to set up. Speedy is just easier to set up. You can see that I have the same style CSS file. I return the same data, and I create my server in a way that it is like HTTP2 enabled, because I mean, by default, the server only supports HTTP1. So to make a server work with HTTP2, you need to enable this protocol support. Now, like in different servers, it is done differently. In Express, for example, you just use this Speedy middleware to enable HTTP2. And also, HTTP2 requires TLS layer because it is secure by default, and it is easier to just generate your like self-signed certificates than make it work without TLS. So I just went ahead and just generated some self-signed certificates for localhost. And actually, that's why if you will be running your demo on yourself, you need to go to this link in your Chrome, and you need to enable. I mean, you need to allow insecure localhost, because otherwise HTTP2 would fail with the SSL protocol error, because by default Chrome does not allow self-signed protocols. But you can enable this for localhost, go into this setting. Now I'm going to, and the client is doing the same thing. It requests 50 files in parallel. And now for this HTTP2 enabled server, if I click on the button, you will see that again, it starts all 50 connections, but now you can actually see that all the connections, I mean, all the requests are served in parallel, and all 50 requests start at the same time. There's no sequential delay. You can see that there is only one connection ID. That's because all the requests are transferred over a single TCP connection now, and this stream of data is multiplexed in a single connection, and actually, since browser supports HTTP2, so browser just, I mean, browser is able to to take this multiplexed stream of data and unscramble it back into the data. It is because browser supports HTTP2. If your client does not support HTTP2, it won't be able to to handle this response, because for such client it would be just meaningless stream of data. And you can see that actually now it uses H2, which means HTTP2. And I think, that's the main part that I wanted to show. I see there's something in the chat. Almost effortless fix. Yeah, right. So basically, in fact, most of the modern clients actually support HTTP2, because HTTP2 was introduced in 2015. Like since then, most of the client libraries, most of the server, I think all of the servers now support HTTP2, and all clients support HTTP2. So HTTP2 at this point should be your go-to version of HTTP, because it actually, I mean, it is free for you. AWS supports it. AWS even supports HTTP3. I'm going on a bit ahead. I will be showing you HTTP3 as well, but AWS supports HTTP3 in services like CloudFront, which is probably the most important for HTTP3. Yeah, so everything supports it. Please, if you still don't use HTTP1, please start using it. It is just enabled in your server, and it just starts working. Okay, yeah. Actually, by default, I think actually most of the servers now use HTTP2 by default, but the common problem across different companies and different teams is that sometimes you just don't upgrade your core dependencies. Sometimes you use web server libraries, like for example, you use Tomcat server, or you use like some Express server from 7 years ago, and that one doesn't have it enabled by default. So just please keep your dependencies up to date, and you will get all the best from the latest update in your dependencies. What's next? Okay, yeah. So now we're coming to the next problem, which I called it long request problem, but really it is a problem that comes from the fact that on your backend you usually not only have some static data that can be served right away, but you also have some background processing. You have some long-running requests. You have some like heavy queries to your database. You have some downstream calls to some downstream services that can work very slowly, and all this latency sums up, and on your client side, you end up waiting for this very long requests, and you basically just underutilize your already limited TCP capabilities. Because, for example, if you only have 6 TCP connections and you're just waiting on some long requests, it means that nothing else is loading in your system. It's the case for HTTP1, but basically, yes, in general. And moreover, this problem is even more relevant if you're switching to event-driven architecture, or you're switching to serverless. Because in serverless world, it doesn't matter whether you transfer data or not. When you're making a request and you're waiting on something, you are basically paying for this idle time. And even if data transfer itself takes 100 milliseconds, and your long request is 60 seconds, you're basically paying for 60 seconds of nothing. And it probably becomes more and more important in the modern architecture. And one of the solutions that I want to suggest, and that I want to talk about, is asynchronous communication. And I want to talk about WebSocket in this case, because WebSocket is probably one of the most popular asynchronous communication protocols. It is fundamentally different from HTTP, because unlike the HTTP that actually based on the stateless request and response, WebSocket actually works atop. It works directly atop of TCP connection, and it establishes the connection between the client and server. There's a special handshake procedure that I will be showing in the demo. But once this connection is established, it basically doesn't use any persistent TCP connection. It is a full duplex communication where both clients and server can actually initiate the request. So server can send request to client over the message. Client can send request to server over the message, and then either of them can respond back. And all these requests and responses are not connected together with the single request response cycle. So it is completely independent. All this messaging happens asynchronously, and without using and which is most important, you don't keep your connection opened while some background processing happens. So you only pay for the for the message transfer time. Yeah, let me just jump to my demo here. And yeah, I want to show you what I have here for demo 6. Again, I use Express, and in this case I use this WebSocket library, which actually integrates with Express as well. So basically, you create a WebSocket server, and you basically attach your Express instance to this WebSocket server, and specifically have 2 things here. So the first one, I want to show you the long polling example, which is the standard way of communicating without WebSocket. So basically, if you don't have a WebSocket connection, what you do is you make a request to the server, and then you just long poll on the response until server is processing something, and then nothing happens for this time, and then server responds you back, and then client makes another request right away and start polling again to get the response message from server. This type of communication is very inefficient. I will show you how that works. And then have another part here which is responsible for the WebSocket connection, and it usually on the callback and event based. You can even see that like everything is based on callbacks. Like you always use, I mean, when you build WebSocket communication, you always use on some event, on another event, on connection, on message, on like one message, on another message, and yeah, everything is event based, and like even the syntaxes reflects this fact that it is a asynchronous communication. Okay, let me just jump to demo. Next one is WebSocket. So yeah, so two examples, the same data, and like our scenario here is that the client makes a request, and then there is a 3-step process on the server, some long process. In our case, server just sleeps, but I mean it can be something useful. So yeah, the client makes a request, and then server starts doing something, and it needs to report in 3 steps. So it basically needs to respond like with the 3 stages of completion. And yeah, let's first see how this works for long polling. So you can see that I'm making my request here. A client waits on it. A server responds after like 3 seconds. The client makes another request, and server responds back with the 2nd step, and finally the 3rd step. And like it takes almost 11 seconds in my case, and like all this time my connection is actually like occupied with nothing, because actually the data transfer here actually takes like 0.19 milliseconds, because it is just like the event, like some callback that needs like to notify your client about something. There's no data. It is just like waste of the connection time. And on the contrast, if I use WebSocket, so I click here, I'm doing the same process. So basically client sends a message to start this process, and now server starts like to respond with the steps. And here's my WebSocket connection. You can see that in the protocol tab, it says that it is a WebSocket. And here, it doesn't use any connection. You can see that it doesn't utilize the connection pool. It is, in fact, it is like out of browser connection pool here. And if you look at this, it uses a special procedure called like a switching protocols procedure, where server responds back. Like a client makes a request to establish WebSocket connection, and client responds back with the 1.1 response switching protocols, and server says that, okay, client, you can upgrade to the WebSocket connection. I basically support WebSocket, and now this WebSocket connection is established. You can see that like a connection, establishing the connection actually takes like, I mean, it is very fast. You just make a call, server opens this connection, and just lets client know that connection is established. And now we go to the messages, because now all the communication happens in messages. There is no response. I mean, no request and response. You just send messages, and like there are like outgoing messages and incoming messages from the client perspective, and from the server perspective, it is the vice versa. You can see that a client sends a special request called long request, which means like just server start this long request, and then server responds with some messages. Message length is like 19 bytes, like very small. Response happens like every 3 seconds. Again, I mean, the whole process takes 11 seconds, but during this time, you don't keep connections open. You don't pay for your serverless lambdas, whatever, like API gateways, and it doesn't occupy any resources. It is like very lightweight, very efficient, and plays really well with the event-driven architecture. Any questions? Okay, I see something in chat. Okay, that's something from the previous. Think any other questions? Maybe any like clarification about this? All right, then I think we can move on. And our next example, okay, And our next problem is like a bit more advanced thing. So like you don't always think about this problem in your day-to-day work, but I called it like network throughput problem, but in fact, this problem is caused by the like constantly increasing amount of communication that we build. Like with the emerging technologies like Kubernetes, like technologies like containerization, like microservice architecture, and similar things. Like we get more and more network communication. There's a communication between services. There's a communication between clients and services. There are like huge streams of data that needs to be sent over the network, and actually sometimes your network bandwidth and your network throughput actually becoming a problem when you have very intensive communication where your requirements to the throughput is really high. For example, in a microservice architecture where services services constantly need to talk to each other at very high speed. You actually need to know that, first of all, that the physical bandwidth of your network is actually limited. So if you have a lot of data or like a lot of requests coming to the single instance of the server that actually are connected to the single network interface that is connected to the single like subnet in your network, you need to know that first of all, the bandwidth of your network is limited. So you can theoretically hit the limits of your network, and the performance of your system will go down just because your network cannot serve it physically. But even if your bandwidth is fine, and it is usually the case, especially if you use some cloud providers like AWS, their networks are like really high bandwidth, like really high quality networks. You still have a problem of throughput, and the throughput is actually related to how you transfer data. So basically, throughput depends on like how you serialize data, like how much overhead in your serialization format you have, like what is the latency in processing. So all these things contribute into your total throughput. And when you have like very high throughput requirements in your system, you always need to think about like how to solve this problem, how to make your data communication more efficient. And I will talk about one particular solution for this, which is called gRPC. And probably everyone heard it before. It is really high performance networking protocol developed by Google initially for their internal infrastructure, but then it actually became like an open standard for like for service-to-service communication, first of all, and like for really like high performance native communication based on the RPC instead of REST API. And like the main goal of gRPC is actually to increase your throughput and to optimize your data transfer and your communication, and make it as efficient as possible. And gRPC achieves that with a few things. So first of all, it uses native serialization instead of like JSON or like similar serialization serialization formats, which means it uses protobuf underneath, and in the protobuf is native serialization format that is supported by most of the languages. And there you can, you just define your protobuf schema, similar to what we did for GraphQL, and then it is serialized into native objects. And in this case, your data transfer is the most efficient because you don't have any overhead on the serialization. So literally, you just pass in the object itself. There's no additional formatting like in JSON. You don't have all this like quotes. You don't have like curly brackets. You don't have anything. It is just like very efficient serialization binary protocol. And it also works at top of of HTTP2, and it actually utilizes this stream multiplexing to avoid all this head of line blocking problems, to support TLS natively, and to implement authentication and like encryption on the protocol level. So everything in gRPC is designed like to be very fast. And in the demo, actually, I won't be showing you like server to service communication, because usually when someone talks about gRPC, it means like server to service communication inside Kubernetes cluster or something like that. But I will actually show you how you can bring gRPC to the web client, and how you can connect from your SPA or from your web application to your service using gRPC, because it is not natively supported by gRPC, but there is a way to do that using a special gRPC proxy, and that is what my demo is about. First, let me show you some code. So in the demo 7, I don't use Express anymore because this one requires like a very special type of server that supports a protobuf serialization underneath, and that actually implements the gRPC protocol itself. And there's a special package called gRPC.js, which is the Node.js implementation for gRPC server. You can find similar implementations for any language, but I use not here, so I use this gRPC.js thing. And in my demo proto, here's my like data definition. So you start with defining your protobuf objects and your protobuf entities, and then you define gRPC services for your entity. So it is basically the interface definition. So once you define your proto file, it can be used as an interface for any language, and like any language you can compile special packages like to implement this interface in your particular language, and you can use it with your particular server in your written in your language. And again, I won't go into protobuf very deep, but again, we have all this like same entities here. We have our profile, our location, and the history entry. And yeah, you can see that in the protobuf definition, you actually define like the positions of your fields so that they can be serialized one after another in a very efficient manner. And sorry. Okay. Yeah, and then you define your methods that actually accepts some parameters and it returns some data. You define input parameter type. In this case, we use empty because we don't actually pass any input parameters. And then you define your output, and you also define whether it is a streamed response or not. And actually, native streaming is one of the features of gRPC, which actually makes it like very cool. Remember, in the example with streaming, we had to come up with our special formats like CSV. You need to think about how you serialize, how you transfer your data, like how you choose this format. In gRPC, it is just supported natively. You define any kind of structure in any kind of object, and you just tell that, okay, so this entity will be streamed, which means it can be a sequence of objects. And then when you're receiving side, you will be just receiving object by object automatically on the native level. It is supported by gRPC. You don't need to invent anything extra. It just works. And I will show you how that works. Yeah, so that's our protobuf definition. And now I just use this definition. I load it, and I just add my service into my server, which will add all these endpoints into my gRPC server. So my server will have get profile endpoint. It will have replication endpoint and get history endpoint. And I just start my server here. And now, yeah, and actually for this case, let me just show you the client side as well, because it is again important to understand like what happens on the client side. So on the client side, again, I have this special precompiled JS files that are actually compiled from the same proto file, but since a client side does not support it natively, you have to use a special library called gRPC Web, and this library basically like transpons all your native representation into JavaScript compatible format. If you open these files, you will see that it is just auto-generated JavaScript definitions for all my entities here. So it's not a native thing, and I mean you won't get these benefits of like native serialization in your browser because it is just not supported. But you can still like make an adapter from the native world into JavaScript world in your browser, and that is done with this gRPC Web library. And then in the demo itself, you will see that I'm using this like pre-generated package to create my demo service client, which is also like pre-generated as a part of it. I connect to my API, and I'm requesting my profile, my location, and I'm requesting the history as a stream. And in JavaScript, it is a regular like Node.js stream type of thing. You just subscribe to the data event, and like in every callback for data, your response is actually an object. So it is already an object. You don't need to like to serialize, deserialize, think about the format. It is just an object that you defined in your proto file. Okay, now let's go to the demo. Okay, so gRPC here, let me clean it up. Network. Okay, so I click here. My server uses HTTP1 because I'm actually not connecting directly to my gRPC server. It is just impossible to connect directly from your browser to the gRPC server. You need a proxy, and in this case, we actually use Envoy proxy that actually supports this kind of like transformation between web format and native gRPC formats. So you can see that I have my proxy in front of my server 7 demo, and I have a special Envoy YAML definition that you can find in the repo as well, that actually defines like how I mean it is a pretty complex thing, but I mean if you're interested in like setting up, you can check the documentation, but basically it says that okay, it needs to map the root road to the demo service, and then it would just be passing all the requests to demo service to my destination, which is like server 7 demo on the port 13007. And that's how this proxy happens from browser. So browser connects to proxy, and proxy connects to the actual gRPC server. And here you can see that, okay, so it is regular request, like everything happens in sequence because it uses the same connection here. Because I'm awaiting, not because, I mean, it cannot use it in parallel. I'm just awaiting it one by one in my example. And if you go to the profile, you will see that actually a transfer happens in the binary format. So this actually a response from my gRPC server proxied through Envoy, and passed in the browser compatible format back to my browser. And if you will try to decode this base64 thing, so let's just try to do it. If you just use some native function, you will see that it is actually the serialized binary data that basically represents your protobuf format. You can see that, I mean, you can recognize some pieces of it because some pieces of it are just in UTF format. Some pieces of it are not supported by browser, so it would just replace it with some bytes. But you can see that it is very efficient. Actually, the length of this message is how much? Length of this message is just 500 bytes. The same for location, and for the history, you see that the response is actually even longer. And if you don't try to decode it as well, it won't even be able to do that because there's a special like streaming format that cannot even be interpreted by the browser. And I mean, you don't have to look into it. I'm showing it just like to showcase you what happens underneath, but in your browser, you will just get this callbacks, and you just need to handle data. So basically, when you're streaming, you just care about the processing. If you want like to do bidirectional streaming, you can actually implement it as well. I'm not doing it here, but you can stream data from the server, and you can stream data back from the client to server, and stream data from the server to client back again. So it can be like a full duplex native streaming, very efficient with like a very low overhead, which actually I mean which ultimately allows you to achieve very high throughput in your network. Yeah, so that's the main thing I want to show. Any questions, or maybe you want to look at something else here in this example, because that is like pretty complicated. Yeah, that is a very good question. So actually, yes, gRPC comes with their own like downsides as well. So as you can see, first of all, the setup may be much more complicated than using of protobufs requires you to think about backward compatibility all the time, because sometimes when you update your format, where especially when you delete fields from your protobuf, you always need to think about backward compatibility, because if you don't think about it, your system may break, because services won't be able to deserialize your new version of the format. And debugging is much more complicated. As you can see, it is not a JSON, it is hard to read. But I mean, again, you just need to think about what's more important for you, the convenience and ease of setup, or high performance, because high performance is not free. I mean, you have to sacrifice something.
I want to add a couple points. If you just holistically to take a look on everything in the industry, you will see that gRPC is a very efficient protocol for communication between server and client, and together with WebAssembly, it allows you to bring native experience to web. Because WebAssembly is very efficient on rendering, and gRPC is very efficient protocol just to pass the data, and you can use any amount of data, almost any amount of data, and cover all of the scenarios by using these two technologies. And because of that, it might be just important to know there is gRPC, and gRPC is very efficient.
Yeah, that's actually a very good point. I didn't explore how you can set it up with the WebAssembly, because probably I would expect that you can even use native protobuf in the WebAssembly and then just proxy it through WebAssembly to browser communication. And in this case, it can be even more efficient, because in this case you don't need all this intermediate format, and you don't need this intermediate proxy. And yeah, let's move on. And okay, last but not the least, this is the preamble to HTTP3, but here I want to talk about the same head of line problem that we discussed in the HTTP level, but now we will be talking about the transport layer, or TCP layer. And this problem is actually more important with the introduction of HTTP2, because now when everything is pushed from the application level to the transport level, so basically what happened in the HTTP is that the application level head of line problem was pushed to the transport level. So it was solved on the application level, because now you don't have this limitation in connections. But there is another more low level flavor of this problem related to the nature of TCP. And the problem with TCP is that by design, the TCP comes with the embedded delivery guarantee, with the embedded ordering guarantee in your packets they transfer over TCP. And when it was created back in 70s, it was fine, and it was actually a very good idea, because you don't need to care about all this consistency of your data. Your packets come in the order, your packets come in with the guaranteed delivery. There's the automatic retry, resend mechanism in TCP. but that mechanism, I mean, as any other guarantee, for example, like as any like delivery guarantee in your message broker, or like a transactionality guarantee in your database, guarantee comes for the cost of performance. Like you always sacrifice performance for some guarantees in a protocol, and here in TCP, this performance limitations come from the fact that TCP transfer happens over the single TCP connection sequentially, and like all the packets come in the same connection. And if some packet in the head of the stream is lost, then by design TCP will just stop all the transfer and stop all the processing, and it will request this packet again, and it will wait for this a corrupted packet or or lost packet, and it will stop all the transfer until the packet is retrieved. And I mean, the cause can be just a lossy network, or just like an unreliable network, or some problems in the communication. But all the transfer will stop, and this introduces like the fundamental limitation for the transfer. And it is the case for both HTTP1. Here you can see how like over HTTP1 these packets come like one after another. In HTTP2 they come multiplexed in the same connection, but the TCP problem is still here. And to address the problem, and it is one of the major features of HTTP3 is the introduction of the new transport layer. So basically, one of the major features of HTTP3 is switching from the TCP transport to so-called quick transport layer, and it is fundamentally different transport layer because it is not based on TCP anymore. Quick protocol is based on UDP, which allows you like to remove this limitation of the guaranteed delivery in transport layer and just multiplex your packets on the protocol level instead of TCP level. So, but let's actually go over like some improvements of HTTP3 compared to HTTP2. So first of all, like yeah, we already talked about the limitation of TCP, and in the quick protocol, it is solved by just removing this guaranteed delivery on the UDP level and just moving all this like consistency and reliability control to the application level where actually quick protocol resides, and then you use very fast underlying UDP connection, and you guarantee your delivery and your your consistency on the quick level, which is like much more efficient than old good TCP reliability control. Another problem and another reason why HTTP2 is still slower than HTTP3 is the TLS, because TLS is not something that is embedded into TCP. When TCP appeared, there was no such thing as TLS, and in previous versions of HTTP and HTTP1 and in HTTP2, TLS is a separate negotiation step. So it is separate from the connection establishment. So your client and the server first establishes the TCP connection, and then there is a separate negotiation step and a separate TLS handshake that happens after your connection is established, and that introduces additional latency and additional delay. In Quick, the TLS is actually embedded into protocol. So during the initial handshake, server would pass all the TLS keys and all the like TLS related data in the initial handshake. So it is basically combining all these two steps together, making it one step, which reduces this latency even more. And yeah, and actually now let me just jump to the demo. In this particular case, I don't use anything on my side. You can see that there's no server for it, because since this protocol is like very new, it is not even a standard yet. So it was started back in 2019. It is still in the stage of like a proposal, but it is already supported by with the major browsers, like by the latest versions of major browsers, for example, Chrome, Firefox, Safari, they all support the HTTP3. And then it is also supported by some servers. Unfortunately, there is no good Node.js server that supports HTTP3, and that's why I could not find anything, and that's why I didn't put anything here. I tried to to spin off a local instance of KD server, which is written in Go, and Go actually supports HTTP3, but I ended up with some problems with the local host self-signed certificates. So HTTP couldn't work on my machine because I didn't have real certificates on my machine. And then I just went on the web and I found this cool page called HTTP3 test servers that actually have the list of publicly available servers that you can use to to test your HTTP3 client. So all the servers support HTTP3, and in my UI, I actually use one of them. You can see that I connect to this quick AO rtc.org, and I request the same style CSS, and that's why I use the content of the style CSS in my previous demo, because I don't control this one and I have to use it, and I wanted to show you exactly the same data and compare it. So you can see that I requested from this server, and yeah, I mean, basically do the same thing, 50 connections in parallel. Let's just jump to the demo, clean this up, go to network, and yeah, demo number 8, HTTP3. So if I click this, you can see that currently everything is served over HTTP2, because by default HTTP3 is not a default protocol. So first time when you connect to your server, it will respond you with the HTTP2, and in the response you can see, one sec, where's the timing? Why can't, okay, oops. Okay, you can see that web server that supports HTTP3 will include a special alt service response header that actually tells client that current server actually supports HTTP3 on port 334, or for example, it supports HTTP3 version 32 or version 29. So I mean, all these are just draft versions of HTTP protocol, because it is still in the design. It has different versions, and different servers supports different versions of HTTP3. And now browser basically knows that, okay, this server supports this, and I can switch to it. So if you will try to request it again, okay, let's actually do this. Oh, actually, let me say, oh, I'm loading from the cache. Okay, one sec, because this is my guest browser, and I just don't use disable cache. So if I run it again, it's gonna load it again. Okay, good. So now we see that there is actually the HTTP3 call. All right, so let's just compare things. So first time we loaded it over HTTP2. It used single connection, as we saw before. The transfer took about 1 second for all these resources, because it opened the TCP connection. It actually negotiated all the TLS stuff. It transferred some data, and the amount of transferred data was 339 bytes, whereas the resource, the actual resource size is just 136 bytes. And now if you compare this to HTTP3, let's check this one. So you can see that the request time is actually almost 5 times lower than HTTP2, because transfer is more efficient. Now the amount of transferred data is much less. It is only 150 bytes, almost equal to the resource size. So there's almost zero overhead for this kind of payload, because I mean, this payload is small and it doesn't require a lot of frames to be transferred. And UDP frame and the quick frame is much smaller than the TCP, a TCP packet. That's why you basically get smaller amount of data transfer, faster communication. No, and you can see this head of line blocking problem here, but it doesn't matter. I mean, it doesn't mean that it doesn't happen here, because basically it's all handled on the TCP level, and it's handled by the kernel. It is handled by the very low level process, and you will never see this head of line blocking problem here in the browser, but it doesn't mean that it doesn't happen. And the fact that this transfer happens much faster, like implies that the transport layer is much more efficient than in HTTP2. And yeah, that's actually everything I wanted to show for this. And that was the last demo. And we can just, yeah, we can just switch to questions and answers. And if you have any questions about this demo, let me check chat.
Mike, I want to thank you because for yourself, it was like around 1 hour, 20 minutes. And for myself, it was riding my bike here, in my office. Yeah, I just burned like 800 calories.
Yeah, very useful, very useful presentation.
Yeah, thanks a lot. It was definitely fun. Join our next event. See you in November. Bye.
Yeah, see you guys.